In this video, we will be talking about velocity and other rates of change. One example of a rate of change is motion along a line, such as a particle in motion or a car driving. In this, position is a function of time. The displacement of the moving object over time is modeled by this equation, which is the change in position equals the function of time plus change in time minus the original function of time. So, to find average velocity of an object in motion, you can find it with the equation velocity average equals displacement over traveled time, which can be expressed as change of displacement over change in time. And then you substitute in your displacement equation for your change of displacement and end up with the final equation of the function of time plus change of time minus function of the original time over the change of time. One of the earliest examples concerned with velocity and acceleration was free fall under the force of gravity. It was found that a freely falling object's distance traveled is proportional to the squared amount of time it fell. This is expressed by this equation. Distance equals half times the acceleration due to gravity times the time traveled squared. So, to find free fall on Earth, we use the equation S equals half 32t squared, where 32 is the gravity constant on Earth. So, in this equation, we find distance in feet by using half times the gravity constant times time squared. Another example of linear motion usage is reading a velocity graph. With these graphs, you can tell when an object is moving forward, backwards, speeding up, slowing down, and standing still. You can also tell from a position time graph what an object's velocity is. You simply take the derivative of each point, which is the same as the slope, and plot it on a velocity time graph. This models a velocity graph, where the y-axis is velocity in meters per second, and the x-axis is time in seconds. As the line moves away from the x-axis, the object is speeding up. If it remains constant, it is at a constant velocity. As it approaches the x-axis, it is slowing down, but still moving forward. Once it crosses the x-axis, at this point, it is at rest, and then begins to move backwards as it is under the x-axis. It is still speeding up as it is moving away from the x-axis, and as it turns, it begins to slow down as it approaches the x-axis, and then stays at rest for the last 5 seconds. This highlighter represents Beth as she jumps out of the plane and free falls into her skydive to the ground.
In the video clip before, you saw the practical application of a free fall problem in Beth's skydive. Here, we will show you how to find the time it took for her to fall from the plane to the ground. So you use the formula S equals 1/2 32t squared, S being the distance in feet, and t being the time in seconds. Here, you plug in 14,500 because that's the distance she fell, and then you take 1/2 of 32, which is 16t squared. Then you divide by 16, and you get 906.25 equals t squared. And then you take the square root of each side, getting plus or minus 30,103 seconds. However, you can't have a negative time, so it would be positive 30,103 seconds.
This eraser represents a car in linear motion. Watch as its velocities and accelerations change.
Alright, so the car, you have to find out when the car is moving forward, backwards, at rest, and when the acceleration is positive and negative. So on the graph, from 0 to 10, it was moving forward. As long as it's over this line, it was moving forward, and it's a positive because the slope is positive. And then it's at rest from 10 to 20 because the slope is 0, and then negative again from 20 to 30 because the slope is negative. And then also from 40 to 50 because the slope is negative. And then since it's below the x-axis from 40 to 50, the car was moving backwards.